All right. So in the first part of the lecture, we managed to obtain estimates in an online fashion. But we assumed throughout that the parameters we wanted to estimate remained constant over time, right? So we were obtaining measurements of the same vector theta. But this is an assumption that does not necessarily hold in practice. So going back to the example of the GPS, its goal is to estimate the location, but the location will typically change over time, right? Because we move. So therefore, we need to extend this framework to accommodate time-varying parameters. So the typical approach to do this is by modeling the time evolution of the parameters by means of what we call a state space model. It is called in this way because the parameters are typically referred to as the state, right? The state of a system, of a dynamical system. And what is perhaps the most common state space model is the linear state space model, right? Which provides this state equation here. In this equation, theta n represents the state at time n, and it is related to the state at time n minus 1 by means of a transition matrix, okay? And this vector C is what we call a control input, right? So it's something that is decided by a controller, perhaps, and it is typically known to us when doing the estimation. So one can think, for example, of a cruise control for a car, right? It sets the throttle to achieve a certain speed. So in that situation, we could think of theta as being the speed, okay, and C as being the throttle. This matrix here captures the how the control inputs translate into changes of the state, right? So for example, if we measure the throttle in let's say liters per hour and the speed in meters per second, then the units of B would be meters per second divided by liters per hour, right? And this matrix is also will also be generally known to us. And finally, this last term captures whatever these other terms don't capture. And if we have done a good job at modeling and there is a little uncertainty in the system, then this should in principle be small, right? This is what we call process noise, right? But depending on the context, it may receive other names, such for instance plant noise, if for instance we are trying to regulate an industrial process, okay? And we can think of it, I mean, in multiple ways, but we can think, for instance, that it captures perturbations that are simply unknown, or we are not measuring, right? So imagine in the case of the cruise control, this could account for the speed of the wind, or perhaps the slope of the hill, or things like that. In this course, we will not be concerned with designing control inputs. This would be something for a course in control theory or reinforcement learning or things like that. So we will absorb these two terms here into a single one that will be our noise process. So this will play the role of the mean of that noise that will be known to us, and then this will be the perturbations around that mean. So this will be the notation that we will choose for the moments of the noise. And as we see, this is a recursive definition, or a recursive equation, because it provides theta n in terms of theta n minus 1, and therefore theta n minus 1 in terms of theta n minus 2, and so on, right? However, this needs to start at some point. So for that, we introduce the initial state, which is time 0. So we assume that things start at time 0, and we model it as a random vector with a certain mean and covariance. Under this setup, the transition matrix will be assumed known. These moments, the moments of the noise and the moments of the initial state, will also be known to us. But so this relates the states, but this we don't directly observe the states, right? So in general, we observe something that depends on the state. So we need a model that relates the measurements and the state. And we will start by looking at the simplest case, which is when the observations are linear functions of the state corrupted by noise. Be aware here of the dimensions. We will use capital D to denote the number of entries of this observation vector. Okay, so this has to be this matrix, the observation matrix has to be D by M. The mean of the noise will be assumed to be 0 as always, and the covariance matrix will be denoted in this way. Both that covariance matrix and the observation matrix will be assumed known. So the goal is as follows. At time n, we observe xn, and our goal is to estimate theta n, but in an online fashion, right? So that means, as we discussed earlier, means bounded memory and bounded computational complexity per iteration. And we will be assuming throughout that the initial state and all these noise vectors, right, the process noise and the observation noise are uncorrelated. Okay, so note that all the other random vectors in this framework are functions of the random vectors here. So these are sort of the primary random vectors, and these ones would be sort of the derived random vectors, right? So it is useful for determining whether two quantities are two random vectors are uncorrelated to express them in terms of these ones here. So I mean, we can think that if we wish to simulate this in a computer, to generate data synthetically, right? Then we would use one random number generator for each of these vectors here. And note as well that be careful with the fact that the notation is very different across the literature. So if you take two books or papers, you will see that what here is what in one of them is they call A, in the other they call it P, and what in one is C, in the other it is Q, and things like that. So it is important to be very careful with the notation. The way this framework is put into practice depends on the specific application, and a certain degree of domain knowledge is typically necessary. I will illustrate this in a specific application, but you need to think how you would apply it in your specific area. So let's consider a 1D model for a drone. This is a drone that can only move vertically, so up and down. The goal is to estimate the altitude, and given the speed of the rotors and given a measurement of the altitude, which can be obtained using one sensor such as barometer or a GPS or ultrasound sensor. It can be also millimeter wave radar, LiDAR, things like that. So let's try to come up with a state equation. So what we need to see here is that the altitude of the drone is governed by the laws of physics, more specifically by the laws of dynamics. And this means that we need to refresh a little our physics from the high school. So remember that in Newton's laws, the force is the mass times the acceleration, and where here n denotes the acceleration at time n times capital T, where capital T is the sampling interval. So as we know, the acceleration is itself a continuous time signal, right? It takes time, it takes a value for all possible time instance, but to work on a computer or a microcontroller, things like that, we need to turn that continuous time signal into a discrete time signal. So if you don't remember these concepts, you can go to the first lectures of this course where we review them. There are two forces acting on this drone. On the one hand, we have the lift, so the force exerted by the propellers, and it points up. The magnitude of this force is proportional to the square of the angular velocity of the propellers, and this is a quantity that the flight controller decides, and therefore we can use it in our estimation. It is known to the drone. And on the other hand, we have a force in the opposite direction, which is the weight. It's mass times the acceleration due to gravity. And by definition, the acceleration is the derivative of the velocity with respect to t, with respect to time, which is typically denoted in this context by v dot. And we now remember that a derivative is just the limit of the difference between the velocity at two time instants divided by the difference between the time instants, right? as this difference goes to 0. So if our sampling interval is sufficiently small, then this quotient here will be approximately equal to the limit, and we can assume that this right hand side here equals the acceleration. Okay. If we now discretize this equation in time, what we find by evaluating it at little t equals n times capital T, this is what we obtained, right? The nth sample of the acceleration equals this expression here, but now we see that these are values of the velocity at integer multiples of the sampling interval. Therefore, we can just introduce this notation, and therefore what we have achieved is to express this discrete time signal for the acceleration in terms of the discrete time signals for the velocity. Okay. So the following the same logic here, we can say that the velocity is given by this function of the altitude. Okay, so of course the altitude is measured like vertically, right? It increases in this upwards direction, but so does the velocity and the acceleration. So this is, as I said, a 1D model. And this collects this or summarizes these equations. The first one is this. The second one is the result of solving this equation for Vn+1, and this one comes from solving this equation for Zn+1. And it can be simplified by solving this one for an and substituting it in the second one, right? This leaves us with one equation for the velocity and one equation for the altitude. This can be expressed in a matrix form in this way. We just need to be careful to write here the correct matrix, right? And we will have this additional term. So now we can recognize this as our state variable, okay? At time n+1, this would be the transition matrix, and this would be the state at time n. This vector here will be this un, and we can possibly add even additional terms that would model perturbations that we are not accounting for here, right? Like changes in the pressure of the air and things like that. So note that one could say that why don't we just apply the same procedure we followed here to reduce these two equations into just one equation. We could, for instance, replace this or solve this equation for Vn and solve and substitute the result here, and that would leave us with just one equation. But then the problem is that Zn+1 will not depend on past quantities. It will also depend on Vn+1, and therefore it is not helpful. Okay, so besides a state equation, we need a measurement equation. And as we said, the altitude is measured by means of a sensor that directly is directly measuring the altitude. It's not so therefore we can write the measurement provided by it as the true altitude plus some noise. Okay, this is a measurement noise. And to express it in the notation of the previous slide, we need to write this in terms of the state vector. So this is the way we can do it. Okay, this is just the state vector, and this is the this would be the observation matrix. Okay, so note that this term here will be fully known. Okay, so this is sort of a model, but I mean deterministic model, but we could add just an additional term for the perturbations. Okay, so now that we know how to formulate a state estimation problem, the next logical step is to solve the problem, right? And to that end, we will be studying the Kalman filter, which is named after this gentleman, although other people have contributed to it. The Kalman filter is an online algorithm to obtain the LMMC estimate of the state at time n, given all the data up to time n. And however, in many books, this is presented as an MMSE estimator, right? But that would involve assuming Gaussianity. So I prefer to present it as an LMMSE estimator, because then we can apply it even if the parameters and the data are not jointly Gaussian, right? And also I think that the math is a little bit more elegant. Let's introduce this notation, theta hat with two subscripts. This indicates the LMMSE estimator of theta n with data up to time n. Okay, and the idea is similar to the LMMSE, the sequential LMMSE estimator that we derived in the first part of the lecture. We start at the nth step. We start from the previous estimate, the estimate of theta n-1 given the data up to time n-1, and we combine it with the data that we receive in this nth step to obtain the next estimate, right? Which will be now the estimate of theta n given data up to time n. So given this data and this data. The Kalman filter is a purely online algorithm, so it means that the computational complexity of this update doesn't grow with n, right? This wouldn't be the case if we were using a batch algorithm. And also the memory requirements don't grow. This means that when we get new data, we just use it for improving the estimate, and then we just throw it away. And it is important to say that the Kalman filter is very well known. It is essential part of the toolbox of signal processing or control engineer, and perhaps also in data science. And it is extensively used by electronic devices, many of those that we have. Although sometimes what they use is are sort of extended versions or generalized versions of the Kalman filter, or at least relatives, algorithms that are related to this one. So let's look at the algorithm, and remember this is the state equation and this is the measurement equation. We have this notation for the moments, and we need to initialize this recursion at some point, which in this case it's time 0, right, for which the state is assumed a random vector with this mean and this covariance. The key idea in the Kalman filter is to decompose this update into a prediction and a correction step. Okay, but before presenting it, let us try to develop some intuition. So here we have this exercise, which is to think what would be your best guess of theta n and xn if you were given an estimate theta n minus 1 hat of theta n minus 1. Okay, so just use intuition. Okay, so this is obviously this is not a question formulated in formal terms, so therefore there's no right or wrong answer, but we just need to think what would be reasonable. So to that end, we just use the same logic as we discussed in the first part of the lecture. Note that theta n is given by this expression. If we didn't know theta n minus 1 and un at all, perhaps our best guess would be like the mean of this plus the mean of this. But if we have an estimate for theta n minus 1, then we can plug it here to obtain an estimate of or a guess. Let's call it guess because this is we are doing it informally. This would be a guess of theta n. Okay, so this is, I mean, like in the example of the bananas. And regarding xn, we will see that xn is given by this expression as a function of theta n, but we are not given theta n, right? What we can do is to use this first expression to find a guess of theta n, and then plug it here to obtain a guess of xn, right? Since the noise has 0 mean, we can just set this to 0, and this would be the natural answer to this question. So let us look at the iteration. This is going to be pretty similar to the iteration for the sequential LMMSE estimator that we saw earlier today. We again start with an initialization, and then at every iteration we will perform the following steps. But remember, we will decompose the iteration into a prediction and a correction step. So this is the prediction. Note that this is the prediction of or the LMMSE estimate of the current state given the past data, right? So although at this point we have already received xn, we are not gonna use it. We just put it aside, right? And we first try to guess what will be the current state, right? So this is what good students do. They first try to guess, think of the answer before looking at the material, right? So after that, we obtain the error of this prediction, like in sequential LMMSE estimator, and that takes us to the correction step. So the correction step has the same form as in the LMMSE, sequential LMMSE estimation algorithm. It is the like the previous estimate, in this case the prediction, plus a linear function of the innovations. Okay, so note that this is precisely our prediction of, or this agrees with our intuition. This would be our coincide with our best guess of xn, given what we knew from before, right? And the matrix multiplying here is called the Kalman gain, right? And that's why we use the letter K, and why we used it before, because it plays the same role. And finally, we obtain the error of this estimate here, right? This is because we will use it in the next iteration. Okay. So it is here. It is not important to remember these equations, but at least to know what are the steps are, and have an idea of what they do, and also to have this intuition, right, to be able to interpret them. Okay. So let us compare the sequential LMMSE estimation algorithm with the Kalman filter to establish the appropriate connections in our brains. And we will do that for the case of a single parameter, and when the observations are scalar value. This is for simplicity, just to focus on what really matters. In the LMMSE estimation framework, the parameter was a random variable, but it was constant over time, right? In contrast, for the Kalman filter, this is allowed to change over time, and we capture the temporal evolution by means of a state space model. In this case, we were given the prior moments of the parameter, whereas here we are given the prior moments of the initial state. Okay, but I mean, this can be thought of as the initial state as well. I mean, it's simply that it doesn't change afterwards. And in addition, here we need the moments of the process noise UN. The observation equations are exactly the same, with the exception that here we have theta, and here we have theta n, right? But for the rest, they coincide. And in terms of notation, here we just needed one subscript, because we just needed to indicate what is the data that we were using. However, here we need two subscripts, because one thing is the time at which we estimate the state, and the other is up to which time instant we consider the data. And the same holds for the variance of the error. So let's look at the iterations. The initializations are exactly the same, and then for every iterate or every iteration, we have that the Kalman filter performs this prediction step, which is not present in the LMMSE estimation algorithm, right? But the next steps coincide. The Kalman filter, the Kalman gain is obtained in the same way, just with the difference in this in the subscripts. The same holds for the correction step, right? it has the same form in both algorithms, although here we didn't call it correction. And finally, the error of this estimate is also obtained with the similar equation. So just by inspection, one may think whether this is a special case of this algorithm here. And in this, indeed, this is the case. So let's suppose that an equals 1 and un has 0 variance. In that case, theta n equals theta n minus 1. So the state does not change, right? So in that case, the model is just boils down to this model here. Let's see if this algorithm also reduces to this algorithm. So here we can see that if an equals 1, then the prediction is exactly the previous estimate, right? And the error is again the same as the previous error, obviously, because if we don't change the estimate, we cannot change the error, right? So this is 0 and this is 1. And then this means that we can just plug wherever it says theta hat n minus 1. So here and here, we just plug in the previous estimate, right? And therefore, if we just identify theta n minus 1 hat with theta n minus 1 given n minus 1, so with this one, then we see that both algorithms are exactly the same. So we see that the Kalman filter generalizes LMMSE estimation for dynamic models, right? Okay, so the Kalman filter relies on the assumption that the state transition model is linear. But in practice, it often happens that this is not the case, and there's some nonlinearity in the transitions, right? So what to do in that case? And what there are multiple possibilities. We are going just to discuss briefly one of them, which is the so-called extended Kalman filter. So here the model is more general than before. The next state is in function of the previous state, but this function need not be linear as before. Note that it should be a function from Rm into Rm, because our state has m entries and it should return something of the same size as the state. This function will be assumed given in the same way as the transition matrix was assumed given for the Kalman filter. And regarding the observation equation, we also allow that the measurements are nonlinear functions of the state. Okay, so here we have another function that is given. In this case, it takes a vector with m entries and returns a vector with d entries. Here we can we assume that this process noise is zero mean, right? This is different from before, where we assumed that it had a known mean. But this assumption entails no loss of generality. So I suggest that you just stop for a minute and think why there is no loss of generality in this assumption. Okay, so the answer is that if this mean were not zero, then we could just absorb it into this function an, right? This function is known in the same way as this mean would have to be known as in the Kalman filter, and besides it is allowed to change over n in the same way as this mean is allowed to change over n in the Kalman filter. So there's no gain in assuming that this is or allowing for this to be not zero. So before we present the algorithm, let us try to use our intuition once more, which will help us decode the algorithm much better. So suppose that we are given an estimate of the previous state, and we need to provide our best guess of the current state and the current observation. So here we can apply the same logic as before. Given this equation, if we have an estimate for theta n-1, it seems natural to plug it here and replace this with its mean, right? And that will give us in our guess of the current state, right? So it would be this one here, and of course this un has zero mean, so even simpler. And regarding xn, we can use this equation. We are not given an estimate of theta n, but we can use our guess of that state and plug it here, and that would return us a vector xn, a guess of xn. Okay. Again, this w has zero mean, just by assumption, in the same way as we said. This is like in the Kalman filter, so the equation simplifies even further. So let's look now at the algorithm. It again starts with an initialization, which is exactly the same as in the Kalman filter. And then for each iteration, we have the following steps. The first one is a prediction step, which agrees 100% with our intuition. And the second one is to approximate the error of this prediction. We see here, I mean, in the past we had here the transition matrix, but now there's no transition matrix. So what we put instead is the Jacobian of this function, right? So this is sort of the closest thing to a transition matrix, right? So it's the matrix in a first order Taylor approximation. So it makes sense. It's a local approximation of the transition matrix, let's say. Then we need to compute the Kalman gain, which is the same equation, but again we don't have, now we don't have an observation matrix, so what we use is the Jacobian of this function here. And then we have the correction equation. Note that the only thing that changes is this expression for the innovations. So this is our prediction for this xn hat, which we see again that it agrees with our intuition perfectly. And finally, we have to approximate the error of this estimate here, and the equation is the same as in the Kalman filter, but now the H is the Jacobian, not the measurement matrix. So this slide is just for you to see that I don't tell you fairy tales. What we study here is used in the real world, right? So this figure here is the architecture of of a flight controller, typically used in drones. And we see here that in one of the modules is an extended Kalman filter, right? This one is used to estimate the position and the attitude of the drone given measurements from a variety of sensors. But I mean, it's not only used in this context, it is used in many others. Okay, so this brings us to the end. We started this lecture by recognizing the key limitations of batch algorithms, and that brought us to the concept of online algorithms. In online algorithms, the memory requirements don't grow with time, and so we just throw away past data. The memory that we need doesn't grow as we receive more data, in contrast to batch algorithms. And besides, the computational complexity per update is bounded, right? So it let's say, doesn't grow quadratically or cubically with the number of samples, for example, as it will do a typical batch algorithm. Another benefit is the low delay. We don't have to wait to collect all the data. And there's even another benefit that we didn't discuss, and that is adaptivity to changes. So, for instance, with the LMMSE estimator, we assume that the parameter that we wanted to estimate remained constant over time. But if it changes sufficiently slowly, right, then we can still apply the LMMSE estimator, and we will obtain reasonable estimates. And this is actually a very common approach in signal processing when we want to track a parameter that changes reasonably smoothly, right? We just find an online algorithm, assuming that it doesn't change, and then we apply it anyway, even though it changes. So it's a common technique. Then we started our journey by deriving the sequential LMMSE estimator. In that field, a key step was the application of the so-called innovations trick, right? That allowed us to use the property of that LMMSE estimators are additive over uncorrelated data, right? So it's a pretty clever trick. Then we moved to the case where the parameters change over time, and that took us to the Kalman filter. We didn't derive the Kalman filter, but since we know how to derive the LMMSE estimator, this is not much more complex. I mean, just as you guys saw, it just involves this prediction step, right? So things are a little bit different, but the core ideas are already present in the derivation that we did. So you are, of course, welcome to take a book and try to do it, do the derivation, but I mean, there's nothing fundamentally new there. Another thing is that we focused on, or we adopted an LMMSE perspective, but as we said, in many books, authors just assume that everything is Gaussian, and then they derive the Kalman filter as an MMSE estimator. But we decided to use the LMMSE approach because it's more general, right? So we don't need that data and the parameters are jointly Gaussian to apply a Kalman filter. And to accommodate the situation where the state transition model is nonlinear or the observation model is nonlinear, we looked at the so-called Kalman filter. The bad news regarding this filter is that there are no performance warranties as in the Kalman filter, so it may work well or it may not. I mean, this typically happens when we linearize things, as you saw we did for the in the iteration of the extended Kalman filter. So what would remain is, I mean, other algorithms for tracking the state of a dynamical system. In this context, famous algorithms are the so-called unscented Kalman filter, also particle filters, and so on. But that is out of the scope of this course. That could make an entire course on its own. So we just presented here the main ideas. If one day you need to do this kind of estimation, you now have the necessary background to read the books that you need. Instead of looking at these algorithms, what we will do in the rest of the course is to at the problem of hypothesis testing, right? Also known as detection in the engineering literature. So we shift gears from the next lecture on. So this is all. Thank you very much for your attention, and see you in the next lecture.